Hello student, today's my topic is dual nature of radiation and matter. Now we start. As we learned previously that the light behaves with the two nature. Sometimes it behaves like a particle and sometimes behaves like a wave. Various phenomena like the diffraction, interference, polarization are explained on the basis of wave nature of light. But some phenomena like the Compton effects and photoelectric effect are explained on the basis of particle nature or the quantum nature of the light. And some phenomena neither explained with the help of wave nature or nor with the particle nature. These phenomena are the reflection and the rectilinear propagation of the light. These are explained with the help of any of these two. So we start. First, when wave interact with itself, then it is wave nature of light. Second, when wave interact with matter, here not with the wave itself. So when it interact with the matter, then it is particle nature. Okay, and the third one is when wave neither interact with wave or particle and phenomenon can be explained by any of these two. Then it is dual. Example for the first: diffraction, interference, and polarization. For the second, these are reflection, refraction, and rectilinear propagation of light. Okay? Now our topic is particle nature of light, means photoelectric effect. Now we have to discuss in detail photoelectric effect. So the next heading is photoelectric effect. Now in photoelectric effect, we have to study in a Coolidge tube, a cathode and anode connected with a battery. Generally, the cathode facing the incoming light waves denoted by H nu. This is the incident light. This plate cathode having work function H nu naught. This is the minimum energy required to emit an electron, and this half mv square is the kinetic energy, remaining energy after H nu minus H nu naught. Means the photoelectric effect means the emission of photoelectron when an incident light is incident on a metal plate, generally cesium. Generally cesium plate, because its work function is very small with respect to other metallic oxides. This equation h nu is equal to h nu naught plus half mv square is Einstein's equation of photoelectric emission, in which h nu is the incident energy or the incident light, h nu naught is the work function denoted by sometime W, whereas half mv square is the kinetic energy. Means when light energy of h nu incident on a metal plate having work function h nu naught, and if h nu is greater than h nu naught, then you get kinetic energy half mv square. Means there is some threshold frequency of metal. If the incident frequency is larger than the threshold frequency, then emission of electron takes place, otherwise not. Okay, these are the photoelectric emission laws. First law is emission of electrons takes place only above the threshold frequency. In this diagram, you can see that initially there is no emission of electron. Electron only emit when it is above the threshold frequency. Means when the incident light is having frequency larger than the threshold frequency, then instantly emission of electron takes place. Second law, photocurrent directly depend on intensity. It does not depend on frequency. In this diagram, you can see that two different intensity 1 and 2 cause two different current I1 and I2, but they have common potential same. Means their kinetic energy remains same. Means kinetic energy does not depend on intensity of light. Only the current depend on intensity of light. In the third law, kinetic energy directly depends on frequency. This is shown by the third graph. In this graph, you can see that two different frequencies causing two different kinetic energy, two different stopping potential, EV0 1 and EV0 2, but they have common current. Means current is independent of frequency. Frequency only changes kinetic energy of the electrons. And in the last photoelectric law, emission takes place instantly as the radiation fall on the metal plate. There is no time lag. There is no time lag. Means instant emission of electron takes place. Now, this is our next topic of photoelectric emission, in which Millikan's experimental determination of Planck constant. Millikan take a rotating drum. This is the arrangement of system. A rotating drum D, which has cylindrical drums coated with alkali metals, and a knife provided which cleans the oxidized layer of the alkali metal. This drum is provided with a negative and positive connections. This is cathode and this is anode. When the incident light H nu hit this alkali metal coating, then electrons emission takes place through the cell, cathode to anode, and this obeys Einstein's photoelectric emission equation. H nu is equal to H nu naught plus half mv square. When the kinetic energy is maximum, then this H nu is known as, then this equation converted into the form of EV naught, that is stopping potential. This maximum kinetic energy is known as stopping potential, that is half mv square is equal to H nu minus H nu naught. EV naught is equal to H nu minus H nu naught, that is V naught is equal to H by E nu minus H by E nu naught. By comparing this equation with the straight line equation y is equal to mx plus c, here potential, stopping potential placed on the y-axis, H by E behaving like the slope, frequency nu on the x-axis, x variable, and minus H upon E nu naught is an intercept. Because this is negative, so this intercept must be on the negative y-axis. With the help of this equation, slope m is equal to H by E, therefore H is equal to E times of slope, and this slope is found with the help of this experiment. So Planck determined value of H with the help of this experiment by plotting a graph, getting the slope, multiplying with E, and the experimental data is 6.6 into 10 to the power minus 34 joule second. This is the value of Planck constant H.